Hi folks. Okay, so if you saw my last video on remote monitoring with the Hach AS950, this diagram will be familiar. In that demonstration, you'll recall that there's a lot of measuring, reacting, and transmitting through wires and pins. In this video, I'll explain how everything is tied together via an Arduino sketch developed for transmitting field conditions to the Internet of Things using a RockBLOCK modem that can talk to the Iridium satellite network, which in turn communicates with Rock7 servers, which then share data with an Internet of Things application like ThingSpeak. As needed, we can configure applications like Twillio in ThingSpeak to send texts to our cell phones when some interesting data is posted to our ThingSpeak channel, or we can configure the Rock7 server to send us all the data via email. Please note that although the respective code is specific to this setup, you can use it as a starter to hack other hardware you might be interested in integrating, such as a tipping bucket rain gauge, a wildlife camera, or a data logger, or just about anything else you might wish to integrate for your invention. The principles for working with these other hardware platforms are very similar to what we'll demonstrate here. The bottom line is that if you can follow what I'm about to explain, you should be able to borrow and hack what I'm sharing for your own applications. The driver that ties everything together will be an Adafruit Pro Trinket running an Arduino sketch. You can use any variant of an Arduino that works for you. I chose the Pro Trinket because it's low power and includes excellent supporting documentation available on Adafruit's website. This slide shows how all our hardware will be wired together. We can now use this diagram to explain how the various components talk to one another. First, let's assume our water sensor is submerged in some water. This causes a rising signal on interrupt pin 3. In response, our ProTrinket pulls program trigger or pin 9 low, which tells the auxiliary port of the Autosampler to start its internal sampling routine, resulting in our Autosampler filling with water. When this happens, the ProTrinket will also communicate with the RockBLOCK modem and tell it to begin sending data to our remote servers for notification that sampling has begun. Once the sampler program is completed, the sampler will take the lead on pulling pin 10 on the ProTrinket low via its connection with the auxiliary port. The Trinket will then signal the RockBLOCK modem that the sampler has completed its program and send a message to our remote servers regarding status and notification. Since I didn't include a screenshot of the wiring on the Autosampler in my last video, here it is. Here you can see my thermostat wire that's connected to my water sensor in the channel. This wire is not connected to the Autosampler, but is eventually tied to the half cable to make routing to the REM a little easier. And here's my sampler tubing in a rodent-proof sleeve. This tubing is how I'm going to get the sample from my channel to the sampler via suction generated by a peristaltic pump on the sampler. And here's the commercial half cable I mentioned in the last video. This is connected to the auxiliary port on the Autosampler and is what we will use to establish communication between the REM and the Autosampler. And finally, all our cables are tied together and eventually guided to the REM via rodent-proof sleeve and conduit. And again, the wiring is fed through conduit to the REM, which is made up of our ProTrinket and RockBLOCK modem. The sketch that we're going to upload to the ProTrinket tells all the hardware how to work together. I'll summarize the most important details of that sketch next, and we'll color code the variables in that sketch for an added dimension that will help tie everything together. Let's go over the color coding first. The sketch we will upload to the Trinket tells all the hardware how to work together. Let's first go over the color coding. Code variables in bold are specific to microcontroller pins used to talk to our sensor and Autosampler. We call pin 9 program trigger, which talks to the Autosampler via the black wire on our half cable. This pin triggers the Autosampler by setting itself low, an action that is registered by the Autosampler as a signal to start its own internal sampling program. We call pin 10 program comp, which talks to the Autosampler via the green wire on the half cable and detects when the Autosampler program is complete. This happens when the Autosampler pulls pin 10 low, an action that takes place for 90 seconds after the Autosampler program has completed. Finally, we attach the half-cable blue wire to the ground pin on our microcontroller. We also have pin 3, which is monitoring the state of flow in our ephemeral wash via our thermostat wire, which is connected to a cheap water sensor, which is powered by the 5-volt and ground pins on the microcontroller. Successful message telemetry requires the ProTrinket to build the message and then wake up the RockBLOCK modem so that telemetry can take place. The modem will then attempt to send the message to satellites that are orbiting the Earth for rebroadcast to the RockBLOCK servers, which can then post it to the Internet of Things. In order for telemetry to be successful, the modem must contact and send its message to the satellite in the short time that satellite is visible above the horizon in its orbit. The variables we'll use to build the message and track the success or failure of our telemetry will be in green font. Since the satellites are visible over the horizon for a limited time, telemetry attempts may fail, so we'll have to write some error handling for when the telemetry isn't successful. If we don't do this, it's likely that we'll have data gaps in our telemetry from failed communications, as was witnessed from pilot testing in one of my prior videos. Code variables that are in blue will be specific to tracking time, environmental conditions such as state of flow, or the Autosampler state. I'll share examples of these next when we start talking about the code. Stepping through the code will be much easier if we can keep these font colors in mind in the following slides. As we already know, our sketches have a pre-setup and loop area where we can define libraries and global variables. Let's start here. We start by including our libraries. Since we're using an Arduino to talk to a RockBLOCK modem, we will need the IridiumSBD library, which is available online via this link and website. A special thanks to Hart for developing and maintaining this library, which enables non-programmers like me to do really cool things with satellites. Since library upgrades can sometimes break code, I will mirror a copy of the version of the library I used with my code on my website included in the description of this video. And here are the variables we'll use to track time. Telem interval and polling interval are variables that we can modify based on our monitoring goals. Telem interval will be used to determine how frequently we send an update to the Internet of Things regarding our field deployment status, such as battery voltage. Polling interval will be used to poll the state of our autosampler once flow has triggered the sampler's internal program and sampling has begun. For satellite communications, Telem interval will have an impact on cost since each data post is billed against credits you purchase from Rock 7. As such, you'll want to set this to a reasonable value that won't draw down your account too quickly. Here it's set to 600,000 milliseconds for my bench tests, which is about 10 minutes. For my field deployments, I set this to 24 hours or 86,400,000 milliseconds since I like the RAM to report on the status of my battery voltage about once a day. For the Hach AS950, the polling interval should be maintained at 60,000 milliseconds, since this checks on the state of the autosampler program once the program is started, and we have a 90-second window to capture that state, resulting from how that particular autosampler is programmed by the manufacturer. I don't recommend changing this for this particular application. Reset loop time and loop start time will help us anchor the state of telemetry attempts and autosampler state in time so that we have a point of reference moving forward. These should be initially set to 0 as global variables. And here are our bold variables related to the microcontroller pins we'll use to communicate with our sensor and autosampler. Program trigger, or pin 9, will be used to trigger the autosampler's own internal sampling program once flow is detected by our interrupt pin. This is done by setting this pin high, which is detected by the autosampler as a trigger to run its program. When this happens, our microcontroller will also instruct the RockBLOCK modem to send a message to the Internet of Things, indicating that the Autosampler program has begun. ProComp, or pin 10, will be used to pull the state of the Autosampler program. Once the Autosampler completes its own internal program, it will pull this pin low for 90 seconds, which will be detected by the microcontroller as a signal to send a message to the Internet of Things that the Autosampler program has completed. And int pin will be used to reference pin 3, which is an interrupt pin. Interrupts are helpful for breaking out of program delays when flow has been detected in a channel. When this pin is pulled high, the rising condition will tell the microcontroller to trigger the Autosampler program via pin 9 by setting that pin high. And here are the variables we'll use to track the Autosampler state. Probe pin status is set to 1 by default and will be set to 0 when the Autosampler program completes. The Autosampler state is monitored via the green wire on the half cable attached to the Autosampler, which gets pulled low for 90 seconds after the Autosampler program completes and then goes back high. Probe waiting will mirror the state of probe pin status. However, once this variable is changed to 0, it is never changed back. This is the variable that positively determines that our Autosampler program is complete. When this variable goes to 0, it's time to come and get your sample. Probe started is set to 0 by default, but goes to 1 if the Autosampler program is started in response to a detected flow event triggered off the interrupt pin in response to detected flow. The setup variable is a flag in our loop to indicate we've just turned on the REM for the first time. We can use this flag to test telemetry immediately for our new installation at the top of our loop. Start code and complete code tell us the state of the Autosampler program. If start code is 1 and complete code is 1, it means we're in the middle of our Autosampler sampling routine. If start code is 1 and complete code is 0, it means the Autosampler program is launched and completed. We'll send these variables to the Internet of Things for tracking Autosampler state online. If our telemetry attempts time out because of poor communication with satellites, the variable timeout is set to true. This is a condition we want to store so that first we can store the unsent message in a holding variable, and then the next time we attempt to send a message, we'll know there's an unsent message in the queue that we should attempt one last try on. My URL is the string that will capture all our data fields for posting on a given telemetry attempt. URL and URL old are the character arrays where our URL strings will be stored for passing to our modem. URL is the current array and URL old is set in the event our transmission attempt times out. Now let's get into our setup code. Setup is that block that will only be run once in our sketch when our microcontroller is just powered on. These first lines will help us determine what's going on in the sketch for debugging. We'll set up a serial connection so that we can monitor the sketch through a serial terminal, report that the REM has just turned on, and then we'll set pin 13 as an output, which is hooked up to an onboard LED by default. This LED will now allow us to monitor whether the RockBLOCK modem is powered on. Next, we'll set up our program trigger pin to be an output so that we can trigger the Autosampler program, and our program comp pin to be an input so that we can detect whether the Autosampler program is complete. Then we'll set the program trigger pin to high, since the Autosampler program responds to this pin when it falls from high to low. In other words, this pin tells the Autosampler microcontroller to start its own program when that pin goes low. Regarding our interrupt pin, we'll set this to call the program begin function when that pin encounters a rising state, which happens when our water sensor encounters water. As a side note, the only available interrupt pin on a ProTrinket is pin number 3. Your own interrupt pin may be different if you're using a different microcontroller, since interrupts are hardwired and cannot be reassigned. The program begin function will be located at the end of our code after the loop block closes, and will be responsible for pulling that program trigger pin low so that the Autosampler program triggers. Next, we'll tell the RockBLOCK what our timeout gap should be. This determines how long RockBLOCK will try to send a message before it times out. In the case of my code, we've set n to be a global variable equal to 25 seconds. If there is a timeout, we'll need to give some time for the RockBLOCK capacitor to recharge prior to its next transmission. The rate at which the capacitor charges will be a function of whether we call the setPowerProfile function with a value of 0 or 1. If powering the sketch from a USB cable attached to a computer, set this number to 1. When you're ready to deploy, you can set this to 0. Okay, everything is set up and we're ready to go. Let's start with the meat of our program, the loop function. First, we'll set the loop start time variable to the time the loop was initiated. This gives us a point of reference in time to gauge how much time has passed for checking conditionals further down in the loop. At this point, our RockBLOCK modem is off and waiting for the right conditions to turn on and begin sending a message. Let's use a conditional to see if the conditions for telemetry have been achieved. Since this is our first go through on the loop, the global variable program started is currently set to 1, so this part of the conditional will allow us to pursue telemetry. Once we're inside this loop, we'll echo some data to our serial terminal indicating that conditions have been met, and then we'll check to see if the last telemetry attempt timed out, and if it did, we'll increase the time for searching for satellites for up to 5 minutes max. Within the conditional, this code starts the process of waking up the RockBLOCK by establishing a serial connection between the ProTrinket and the RockBLOCK modem. If the wake-up procedure is successful, we set digital pin 13 to high. Pin 13 is tied to an onboard LED on the ProTrinket that will glow red. This gives us visual confirmation that the RockBLOCK awoke OK, in the event that we are in the field and not tethered to a computer via a serial connection. If we don't see this LED come on after a few minutes, we might have to reposition our hardware in a different location with better visibility of the sky. Next, we can call some sensor functions and store results in string variables. In this case, our trinket is pulling the voltage of our LiPo battery and storing the results in the string variable myvolts. Prog started and prog waiting are global variables set to 0 and 1 initially, but over the course of time, these variables will be updated depending on whether the Autosampler program has started and when the program completes. The respective numbers are converted to strings, start code and complete code, for embedding in a URL. And this is where the URL is put together from the respective strings tracking battery voltage and the Autosampler program state. The string is then converted to a character array, which is the type of data used by the RockBLOCK modem for sending data to its servers. Before we send current data, let's check for any old data that didn't make it. If the timeout variable is set to true, that means that the last attempt failed. In this case, we call the message retry function. The message retry function will then try to send the last post that failed stored in URL old 2 more times. Regardless of whether the old message was sent successfully, we'll return to the main loop from message retry and set the timeout variable back to false. Next, we'll try to send the current data via the adaptive retry function. Adaptive retry will try to send the latest data via this line of code. This will be attempted several times via a for loop, with the interval between each try increasing over time. If the telemetry fails on the 5th try, the timeout variable will be set true. Otherwise, it will remain false. Either way, we will break out of the loop. You'll notice there's a handle message function here. This is for handling incoming messages sent by a user online, which is useful for changing telemetry intervals and other variables remotely. I'll cover this in another video at a later date. If the message timed out, then this conditional will save the old message to URL old for a telemetry retry upon the next loop iteration. Once our telemetry attempt is completed, these lines power down our modem and we set our status pin low for visual confirmation that the modem is powered down. Okay, we've attempted some telemetry. Let's settle all our variables and store what's happened. Note that we'll return to the top of the loop once our telemetry interval has expired. Take note that all this activity executes only if the conditionals for telemetry are met. In this case, we step through the conditional because our setup variable was equal to 1, indicating that our remote environmental monitor had just been turned on and wanted to send a message to test connectivity. Other conditionals that can prompt telemetry via this conditional include my telemetry interval having been exceeded and/or the Autosampler program has started and/or the Autosampler program has completed. Let's assume that those conditions were not met at the start of the loop. In that case, this else block is implemented. When in this block, we enter a while loop that won't allow us to return to the top of the loop until our polling interval has expired. While in the polling interval, we'll call this program complete function. Program complete is a function that polls the state of the autosampler and sets the prog waiting variable to 0 in the event the autosampler happens to be running its own internal program. If either the prog started variable is set to 1 from the interrupt function being triggered, or prog waiting is set to 0 because the autosampler program is completed, then we'll break out of this while loop. Back at the top of our loop, we'll check our main conditional to see if we can initiate telemetry. If any of our conditionals are met, we'll proceed with the associated block, which will attempt to send any old messages in the queue, any new messages reflecting our most recent data, or store our most recent data for a later attempt in the event telemetry isn't realized. Let's wire things up to a breadboard and give it a spin. Here you can see that my orange wire is tied to pin 3, which you will recall is my interrupt pin. Notice that this pin is pulled low off my breadboard power rail cathode, just as if it were attached to my water sensor. As a side note, the reason I don't hook up the orange wire to the terminal block you see here is that the respective post is bad. Moving on, next I have a black wire attached to my program trigger pin, which is pin 9 in my code. This pin is defined as an output pin with a default setting of high, and which I'll pull low when I want to trigger my autosampler program. I'll demonstrate how this happens in a second. Finally, I have a green wire attached to my prog comp pin, which is pin 10 in my code. This pin is defined as an input and is pulled high by the autosampler via the half cable. In this case, I just have it attached to the positive rail on my breadboard to simulate the same. So, in order to simulate flow, let's move my orange wire to the anode rail on my breadboard. This is like closing a switch on a water sensor, which results in pin 3 getting pulled high. Because pin 3 is an interrupt pin, I've programmed it to react when the voltage is rising. When that happens, the ProTrinket stops whatever it's doing and immediately calls the program begin function. This function pulls the program trigger pin low, which, when attached to an autosampler via half cable, will signal the autosampler to start its own internal sampling program. You can actually measure this by attaching a voltmeter to that lead and ground and watching what happens when you pull the interrupt pin high. When this happens, the REM will also send a message out to its servers noting that the program has started. Once the autosampler program completes, the autosampler will signal the REM via the half cable by pulling prog comp pin low for 90 seconds. That is detected by the green wire in this demonstration. We can simulate that happening by attaching that green wire from the anode to the cathode rail of the breadboard. This action will trigger the REM to send a message to our servers, indicating that the autosampler program has completed. So the state of all those pins is stored in a URL variable in our code and eventually posted to the RockBLOCK servers, where it's relayed to ThingSpeak. The following slides present screenshots of a ThingSpeak channel set up to receive field data from our programmed REM. This shows the effect of pulling the orange wire on interrupt pin 3 high, resulting in the start code graph registering a value of 1 or true. When this happens, we have background applications like if-then and Twillio running in ThingSpeak that will send a text to our cell phone, but more on that in another video. And should we have one available, this is how those actions are registered in a serial terminal, both the flow detection and the telemetry attempt. After the post, our sketch is still waiting for its routine telemetry interval to expire, which in this case is set to post every 10 minutes. Our timer expires 3 minutes after our recent flow notification, so the REM posts its regular data point here. The program start code is reset to 0 here since the threshold for sending notification of program start has already passed. This will avoid problems with other conditionals later on in our loop. And here is what the serial terminal looks like when the monitoring interval has exceeded and another attempt at telemetry is made. Next, let's pull pin 10 low by attaching it to the cathode rail. This is what happens when the Autosampler program is completed and signals the REM to address telemetry. We set Twillio triggers to send us notifications according to these 2 points. And here's one more test with a longer interval to simulate an Autosampler program that is running for a few hours. Here you can see that from start to finish, 7 hours and 17 minutes have passed between the 2 trigger events, one for flow and one for the Autosampler program completing. The results I just shared were generated with the sketch and hardware setup outlined in this video. I'll do a real-time demonstration of what I've just described in a future video. So in closing, this video covered how to code an Arduino type microcontroller to use a RockBLOCK modem to send data to a ROC7 server using the Iridium satellite network. In my next chapter, I'll summarize how to configure the ROC7 server to send data to your ThingSpeak channel for viewing online. We'll eventually cover how to use the Twillio application within ThingSpeak to post selected events to your cell phone for immediate response. Before ending, I want to acknowledge and thank Sean Keane, who worked as an intern for my agency. Sean helped us figure out how to integrate the Hach AS950 with an Arduino, and also work with the ROC7 technical support folks on error handling for drop telemetry. Also, thanks to the technical support team at ROC7 for always promptly getting back to myself and Sean with helpful guidance in response to our questions, and also for setting up their servers to work with ThingSpeak. Finally, thanks to Hach for answering our questions on how to interface an Arduino with the AS950 auxiliary pins. More details are coming soon. Stay tuned, and thanks for watching.